Hello everyone, welcome back to the channel. This is part 9 of a video series where I'm attempting to explain every Sudoku solve technique. In parts 1 through 8, we covered basic techniques, advanced groups, fish, single-digit chains, multi-digit chains, forcing chains, coloring, and patterns, respectively. And in this part, we're going to be covering uniqueness techniques. So in the last part on patterns, we focused on really any techniques that are reliant on a specific state of the grid where we can make eliminations based on a pattern or at least draw some correlations between the different placements based on a pattern. And some of these techniques were focused on what we can call deadly patterns, which are states of the grid that leave us with no valid solutions. In this video, I want to focus on a different type of deadly pattern where a certain state of the grid leaves us with multiple equally valid solutions. So let's get into a little bit more about how that works. Uniqueness techniques in Sudoku are based on the idea that a valid puzzle must have exactly one solution. This isn't as universally accepted as the constraint that every house must contain the digits 1 through 9 exactly once, but generally the Sudoku community has come to view this as a valid constraint of a good puzzle. And the reason this is because if we have multiple different valid solutions, then we can't get to a finalized completed grid without making some completely arbitrary assumption at some point. So here we have an example of a grid that has multiple different solutions, and we could see it is almost completely solved out except for these 4 cells right here. And you'll notice these 4 cells are in 2 boxes in the same band. That'll become important later when we go through some of the techniques. But they contain the candidates 3 and 5. However, you'll notice there's no additional information that tells us which of these cells is actually a 3 and which of these cells is actually a 5. We could say that these 2 cells are 3s, and these 2 cells are 5s, or vice versa, these 2 cells are 5s and these 2 cells are 3s. Both of those are equally valid, and there's nothing telling us one is more valid than the other. So we can't get to a completed grid using logic alone. We have to make some kind of arbitrary assumption. And if you can't complete a puzzle using logic alone, then it's not really a valid puzzle. So if we're operating under the assumption that our puzzle is valid and it does have a unique solution, what we could do is use techniques to avoid any circumstance where we would have this pattern that would make it not unique. And that is the premise of uniqueness techniques. So let's get into how to use them. Avoidable rectangles are one of the simplest techniques, and they occur when we have that deadly rectangle pattern we just looked at, and we start to fill it in, but we could stop it from being completed by preventing at least one of the placements of the candidates. So here we have a grid from Sudoku, and one thing you might notice is some of the numbers here are blue while others are black, and the reason that is because avoidable rectangles are one of the few techniques where we have to distinguish between numbers that were given to us from the start and numbers that we placed due to some kind of deduction. So in this case, the black numbers are numbers that were given to us at the start as clues, and the blue numbers are ones that we deduced. So let's go ahead and take a look at these 4 cells right here. We could see we have the candidates of 7 and 9 already filled in 3 of these cells, and in this last cell, we have the option to place a 9. Let's just go ahead and assume that the 9 is there. What we would have here is that same deadly rectangle pattern, where we have 2 candidates that are in these 4 cells, which contain the same, which are limited to 2 boxes, 2 rows, and 2 columns. And the reason this is deadly is because this 9 and 7 end up being completely interchangeable when we have them in the pattern like this. So if we know a 7 and 9 are going to be here, it doesn't matter to the rest of these cells in the box which one's 7, which one's 9. Doesn't matter to the rest of the cells in this column which one's 7, which one's 9. And since we know we have 2 sets of these 7 and 9, and they're in the same 2 rows, it's not going to matter to the rest of the row which one is 7, which one's 9. So since it doesn't matter to any other cell, these end up being completely interchangeable. But since we know they're not interchangeable because we place them in specific locations, we could actually make the deduction that a 9 will not be in the cell so that we don't get that interchangeable pattern. So an important thing to note is that this technique only works if all of the filled in cells are not given to us from the start. Because if one of them was given to us from the start, that would essentially fix it in place and make it non-interchangeable, which would destroy the whole premise of the technique. So in Sudoku Coach, that would mean we have to be only working with filled in cells that are blue instead of black. So that's how we would do an avoidable rectangle where we have 3 cells that are already filled in, but we could also do it with less cells filled in. Here we have another example from Sudoku, and let's go ahead and take a look at these 4 cells right here. So again, it's in the same pattern where we have 4 cells in 2 boxes, 2 columns, and 2 rows. And we could see 2 of these cells are filled in with a 3 and a 7, and these 2 cells both have candidates of 3 and 7. But there's one additional candidate, and that is the 9. If the 9 wasn't there, you'd have this same deadly pattern here of 3, 7, 3, 7. And in order to prevent that, we know 9 must be in one of these 2 cells. Therefore, we could eliminate any 9s that see both of these cells. So that would be all of these 9s right here. We could go ahead and eliminate those. So we could even do this if we only have one cell filled in. Let's say this 7 was filled in, and this cell right here had a 3 and a 9. Well, we would be left with the same situation. One of these 3 cells would have to be a 9. And so any 9s that see all 3 of these cells can then be eliminated, because that would force a deadly pattern. So if we had this situation, we could eliminate this 9 right here. And that's how we do avoidable rectangles. Unique rectangles are also focused on avoiding that deadly rectangle pattern, but unlike avoidable rectangles, none of the cells are filled in. Instead, we will have at least 2 of those cells be BUG-Value, containing the 2 candidates for a deadly pattern. And what we want to do is prevent the remaining cells from also being whittled down to those 2 candidates, or else we'll run into a situation where we have those 4 BUG-Value cells, and they're completely interchangeable, so there's no more logical deductions we can make from that. So there are all sorts of ways that we could do unique rectangles. Depending on who you ask, there's 5 or 6 different types. So I'm going to try to go through each type relatively quickly. So starting off here, we have a grid from the Sudoku wiki, and all of the unique rectangle grids are going to be from the same Sudoku wiki article. And this is a type 1 unique rectangle. It's the simplest one because we have 3 BUG-Value cells. So you can see here our highlighted cells, 3 of them contain the values 2 and 9. So if this last cell was to contain 2 and 9, we would have a deadly pattern, and we couldn't make any deductions from here. So in order to prevent that from happening, we could eliminate the 2 and the 9 from this cell. So this is a type 2 unique rectangle, and in this case, we will have our 2 BUG-Value cells will be aligned with each other, and we will have a third candidate in the remaining 2 cells. So you can see we have 1 and 5 in these 2 cells, and we have 7 in addition to the 1 and 5 in these 2 cells. Now what we could do is any 7 that sees both of these cells can be eliminated, because if a 7 was to see both those cells, that would force us into a deadly pattern. So that would be these 2 7s right here that we can eliminate. Now we could also do the same situation where our BUG-Value cells are diagonal to each other. Some sources consider this to be a different type, though they would call it a type 5 unique rectangle, but fundamentally I think it's the same technique. So here's a type 3 unique rectangle, and the cool thing about type 3 is that it takes advantage of naked subsets. So we can see here we have our 2 aligned BUG-Value cells, but in our 2 remaining cells we don't just have a third candidate, we have 2 additional candidates, a 1 and a 7. So what we can deduce is that if any placement would force a 1 and a 7 to be to see both these cells, then we could eliminate that placement. And we could actually see here that we have a 1 and a 7 in this cell. So if we were to have a 1 and a 7 in addition to that in one of the remaining cells, that would force the other candidate to be a 1 or a 7 here, and that would get rid of the 1 and the 7 from these 2 cells. So essentially what that means is we could eliminate any 1s or 7s from our remaining cells here. So here we have a type 4 unique rectangle, and this occurs when we have 2 aligned BUG-Value cells, and one of the candidates in the remaining cells with extra candidates is restricted within that row or column. So in this case, we have 6 and 7 in these 2 cells, and we have a bunch of extra candidates in these 2 cells, but we'll notice our 6 has to be in one of these 2 cells because those are the only spots for it in the row. So if a 7 was in one of these cells, it would force a 6 to be in the other one, and then we would be completing that deadly rectangle pattern, which we must avoid. So what we can deduce from that is 7s can be eliminated from both of those cells. So here is a very similar technique. This is a type 5 or 6, depending on who you ask, unique rectangle. And here we will have our two bi-value cells are diagonal to each other, but one of the candidates is restricted in both of the lines. So here we could see we have 2 and 8, and these are diagonal to each other, and then we have these two cells with extra candidates. But if we actually look at the placements of the 8, we'll see that it's restricted in these two lines. So there's going to be an 8 in one of these two cells and an 8 in one of these two cells. And what that means is if we were to place a 2 in this cell, that would force an 8 to be here and here, and that would force a 2 to be here. And that would create that deadly rectangle pattern. So what we could do is eliminate the 2 from both this cell and this cell. And then finally, this is the last type of unique rectangle I want to cover. It's considered a type 2 rectangle in the Sudoku wiki, but I think it's completely different, so I wanted to cover it separately. This is interesting because it takes advantage of almost hidden sets. So we can see with our 4 cells here, we have 3 and 6 that are aligned by value cells here, and then we have some extra candidates in these two cells. However, if we look at the placements of 3 and 6 in this line, we'll notice that 3 and 6 are restricted to these 3 positions. So this ends up being an almost hidden pair. If we were to have one of those positions removed, then that would make the 3 and 6 a hidden pair. So what we could do is we could eliminate any additional candidates from this extra position here. Because if this position was filled, then 3 and 6 would be forced into these two spots, and that would create a deadly rectangle. So we could eliminate the 4, 5, and 7 from this cell. And that is all the unique rectangle techniques. Hidden unique rectangles are very similar to regular unique rectangles, but our deadly pattern is buried under some additional candidates, and we only need one bi-value cell to use the technique. So here we have a grid from the Sudoku wiki, and we can see these 4 cells that are highlighted. Only one of them is bi-value. It contains a 6 and an 8, and those are going to be the deadly pattern candidates we need to worry about. And we can see the 6 and 8 are also candidates in the remaining 3 cells too. So none of the unique rectangle techniques would work here because we only have one bi-value cell. But if we look at the positions of our 8 and our 6, we might notice that the 6s are restricted to 2 positions in this column and 2 positions in this row. So this 6 is strongly linked to these two 6s. If it was not there, these two 6s would be forced to be true, and that would force the 8 to be true. So if an 8 was in this cell, and therefore forcing the 6 to be false, that would create this deadly pattern. So what we could say is that the 8 can be eliminated from the cell. So to summarize all of that, the non-restricted candidate can be removed from the cell opposite to our bi-value cell. And that is how we would do a hidden unique rectangle. Extended rectangles, as the name implies, allow us to extend our deadly rectangle pattern to all 3 boxes in a band. So before we get into what that looks like in terms of an actual grid, let's go ahead and just prove that this is still a deadly rectangle pattern. So we can do this very similarly to how we proved our 2x2 deadly rectangle pattern. I have an empty grid here, and we have these 9 cells that are marked. And we can see that they can only contain the candidates 1, 2, and 3. So knowing that, we could say that in this column, there will be a 1, 2, and 3 because there are 3 cells, so that forms a naked triple. And we could say the same thing about the other 2 columns. Therefore, the candidates in these remaining cells will be completely unaffected by which one is a 1, which one's a 2, which one's a 3, because there's going to be a 1, 2, and 3 either way. We could say the same thing about the remaining cells in this box. We know there's going to be a 1, 2, and a 3 in this box, so it doesn't matter if this is a 1 or if this is a 2 or if this is a 3. And we could use the same logic about the rows. So since all of these cells outside of this 3x3 pattern are unaffected by the actual contents of the pattern, then it's arbitrary what the actual content is. So This is the same situation with a 2x2 rectangle just scaled up to 3x3. And when we have this situation where the cells outside the pattern are completely unaffected, this is called an impermeable deadly pattern. But we could also have a situation where these cells outside are affected. Let's say if we removed one of these columns, I'll just go and remove this middle one, but it doesn't matter which one. This would actually still be a deadly pattern. And I'll go ahead and prove that in a second. But this is permeable now, because if I was to place a number in one of these cells, let's say I placed a 1 here, that would actually affect the pattern. Now we could only have a 2 and 3 here. Same thing if I placed a number in any of these other cells. The cells here now interact with the cells here. Same thing for the rows. The columns will not interact because we still have a naked triple, but the rows and box cells will still interact. So you might be saying, okay, how is this a deadly pattern if outside cells still interact with the pattern? And that's because we could actually find two versions of the same pattern that are equivalent to all the remaining cells, which means the choice is arbitrary. And let's go ahead and prove that. So let's say we were to place a candidate in one of these cells. Doesn't matter which one, but I'm going to go ahead and place a 1 in this top left cell. Now this leaves me with two options for where to place the other one. I'm going to place it right here. Now let's go ahead and fill a number in this cell. Let's say we place a 2 because we already used up a 1. That forces a 3 here, and then we can complete that pattern. So that is one distribution of candidates that we could have. And you'll notice that we have a candidate in this first and third box on the outsides here. I'm going to go ahead and highlight that in yellow. Then we have a candidate in the top two boxes. I want to go ahead and highlight that in orange. And then we have a candidate in these bottom two boxes. I want to go ahead and highlight that in red. So I want to go ahead and delete the actual candidates in this cell because really I just want to look at the colors. That'll show us the distribution of the candidates for that pattern. So that's one way we could do it. Now I'm going to go ahead and replicate the pattern in these cells right here. And let's go ahead and place candidates differently this time. So we'll still place a 1 in the top left here. But instead of choosing to place it down here, the second one I'll choose to place here. And again, that's the only choice I can make once I place a 1, because the rest of the candidates end up just falling into place. So if I place a 2 there, that forces a 3, 3, 2. Okay. Now we have a similar pattern. We still have a candidate that is in the first and third box on the outsides. I'll highlight that in yellow. We have a candidate which is in these top two boxes. So I'll highlight that in orange. And we have a candidate that's in these bottom two boxes. I will highlight that in red. And now let's go ahead and delete the actual candidates themselves, because again, those are arbitrary. And we could see we have these two patterns for how we could distribute candidates across this template here. And we could see, even though they are different, this row and box still contains an orange and a yellow. This row and box still contains an orange and a red, and this row and box still contains a yellow and a red. In fact, these are just the same pattern reflected vertically. So we could see from this that we can fill that pattern in two ways that are equivalent from the perspective of the box and the row. So we could do our 1s here, our 2s here, our 3s here, or our 1s here, 2s here, 3s here. The box and the row see these as being completely equivalent, even though it still interacts with the box and the row. So this is how we could have permeable deadly patterns. And this 2x3 formation is going to be a lot more common than the 3x3 formation that we went over earlier when it comes to extended unique rectangles. So now let's go ahead and get into what that looks like in terms of an actual grid. So here we have a grid from the Sudoku wiki, and we could see with our highlighted cells here that we have that same 2x3 cell pattern that we just went over. And these 6 cells contain the same 3 candidates, 1, 3, and 5, with the exception of this top left cell, which also contains a 6. If this 6 wasn't here, we would have that deadly pattern. So just like what we did with type 1 unique rectangles, we could eliminate our deadly candidates from this cell here. So we could eliminate the 1 and the 5 in order to break our deadly pattern. So that is called a type 1 extended unique rectangle, and the other types of extended unique rectangles have analogs as well. Binary universal graves are what happen when we extend a deadly pattern to our entire grid. And this happens when we have every cell, every remaining cell in a grid has 2 potential candidates, and each instance of those candidates appears exactly twice in each house. So here we have an example. This is a grid from Sudopedia of a bug. And we could see every cell here has two values. And if we look at any specific candidate, let's take a look at our ones, we can see that each one appears exactly twice in each box, in each row, in each column. And we could check this for all of the other candidates here. So this is what leads to the name. Our binary options, we only have two options, is universal to the whole grid, and this leads the puzzle to its grave, because this is a deadly pattern. And the reason this is because if every single constraint has exactly two possibilities, each cell has two possible candidates to fill it, and each house has two possible positions for each candidate, then there's no way for the puzzle to distinguish which of those two possibilities is more valid, and therefore we would have a non-unique deadly pattern. So we need to avoid this kind of pattern occurring in a puzzle at all costs. So what we'll see is sometimes you'll have a guardian. So for example, let's say we had a 9 in this cell. This would be guarding us from having a bug. And when we only have one guardian, that's called a bug plus one. And so these scenarios, it's really easy to identify which cell has our guardian because it will be the only tri-value cell in the entire grid. So we could very easily tell this would be our guardian cell. And then we could tell which candidates are guardian by counting how many times each candidate appears in a house. And it doesn't matter if we count the rows, columns, or boxes. We'll get the same result either way. But if we count the number of fives, we can count two fives in this row. We can count two sevens in this row. But our 9 appears 3 times. So that's the odd one out. So we could tell that 9 is our guardian. If 9 was not here, then every candidate would appear twice. So in order to kill our bug, we would have to place a 9 here. So that's a bug plus one, but we could also have it when we have more guardians. So here we have another grid where we're almost at a bug, but we have two tri-value cells, which means two guardians that are preventing us from having a bug. Let's take a look at this cell. If we look at the rows, we see that 8 appears twice, 9 appears twice, and 7 appears 3 times. So 7 is going to be one of our bug guardians. And then if we look at this row, we could see 1 appears twice, 7 appears twice, but 8 appears 3 times. So 8 is going to be our second bug guardian. So if there was a candidate that would take both of these guardians out at the same time, then we could eliminate that candidate. So if there's an 8 in this cell, for example, that would eliminate the 7 and the 8 here. So we know that 8 can be eliminated because it would kill both our guardians. And if there's a 7 in this cell, it would do the same thing. So the 7 can be eliminated here as well. So that is how we handle bugs. A BUG-Lite is essentially just a bug that hasn't made it universal. So we still have a bunch of bi-value cells where each candidate appears twice in its house, but it's only occupying a portion of the grid, typically in more than just one band. So we could think of BUG-Lites as somewhere in between deadly rectangles and bugs in terms of deadly patterns. So here we have a grid from Sudopedia, and this is an example of what a BUG-Lite might look like. We could see that we have all these highlighted cells are bi-value, and each of the candidates, 4, 6, and 9, appears exactly twice in each of its houses. So BUG-Lites are a little bit tricky to spot, but one way you could do it is since they are all bi-value cells, and it's an impermeable pattern, if you're starting to notice that you have a lot of naked pairs that are only interacting with each other, but not interacting with the rest of the grid, there might be a chance you have a BUG-Lite on your hands. So let's say that we haven't reached this impossible state of the grid, and let's say we have a couple guardians. So I'm going to go ahead and put some guardians in these cells and unrestrict our 9s here, just so the puzzle makes a little bit of sense. This was the original grid on Sudopedia. This would be a BUG-Lite plus 2, because we have these two tri-value cells and some two guardian candidates that are stopping us from having that BUG-Lite. So we could see those guardian candidates are 1 and 3, because those appear more than twice in their respective houses. So anything that would eliminate both this 1 and the 3 can then be eliminated. So there aren't really any candidates that directly do that, but we could see that our 6 here is restricted to these two cells in the house. So if a 9 was placed in one of these cells, it would force a 6 into the other cell. Similar to how we did type 4 unique rectangles, we could say that these two 9s can then be eliminated because they would force a 6 to be there. So that is an elimination we can make to avoid our BUG-Lite in this scenario. Multivalue universal graves, or MUGs, are what happens when we have a global deadly pattern with more than two candidates per cell or more than two placements per house. And just like bugs, MUGs can also have a light version, which doesn't necessarily extend to the entire grid. There's a lot of reasons why MUGs are actually quite a bit trickier to deal with than bugs. First of all, it's harder to verify that you have a MUG. With bugs, you could just check that all your cells are BUG-Value, and each candidate appears twice in its house. However, this is not the case with MUGs, and we actually have to look at the shape of the pattern to verify that it is a MUG. Also with bugs, if we are in a bug plus one or bug plus two situation where we haven't quite gotten to the deadly pattern, we could very easily identify the guardian candidates by looking at which cells are tri-value. They'll stick out like a sore thumb. However, with MUGs, since every cell in our pattern can theoretically have a different number of candidates, we can't use candidate counting to determine which cells contain our guardians. So with MUGs, we really have to understand the underlying deadly patterns to figure out if we have a MUG and what candidates we need to eliminate to avoid that MUG. So here we have a grid that was posted by MythJellies on the new Sudoku Players forum, and we could see in our highlighted cells that we have a lot of BUG-Value cells with 4 and 8 or 2 and 8. And at first, this might look like we have a BUG-Lite plus 2 on our hands. After all, we have a bunch of BUG-Value cells and 2 tri-value cells. However, this 1 sticks out like a sore thumb, and we'll find that if we were to remove this 1, we would already have a deadly pattern, even though we still have 1 tri-value cell left. So we could look and see that all of our candidates that are remaining are in locked sets. We have a 4 and an 8 naked pair in this column and box, and then we have a 2, 4, 8 naked triple in this column, box, and row, and then a 2, 8 naked pair in this row and these two columns and boxes. So this is a completely locked set, completely interchangeable. So this is an impermeable deadly pattern. And we could actually see that this is what happens when you overlay a deadly rectangle with 4 and 8 with a bent deadly pattern of 2 and 8, which are both two simpler deadly patterns. And the overlap cell is what creates this tri-value cell that's participating in both. So if we were to place the 1 back in this cell, this would actually be a BUG-Lite plus 1 situation. And in order to break this BUG-Lite, we would have to place a 1 in this cell. So that is what an impermeable BUG-Lite looks like. And one of the ways we could spot it is the fact that we have all of these locked sets which aren't interacting with anything else on the grid. However, we also can run into permeable MUGs, which are even more difficult to spot. So in another post, MythJellies listed a bunch of different permeable MUG patterns. This is one of them. This contains the candidates 1, 2, 3, and 4, and it's spread across 8 cells. And we can see it's permeable because the number of candidates doesn't necessarily equal the number of cells in a house. For example, this column has 2 cells in the pattern, yet it has 4 candidates. So if we were to place a 3 here, that would affect our pattern differently than if we were to place a 2 here, for example. So we're not going to exhaustively prove that this is a deadly pattern. However, we could see that no matter what candidates are eliminated, there are several different options for simple deadly patterns that can be made in this grid. For example, let's say we had a 1 and a 2 in this cell. We're going to have two candidates, two different candidates, so it doesn't really matter which ones. We can make a deadly rectangle using this 1 or 2, or using this 1 or 2, or we can make a bent deadly pattern using this 1 and 2 and 1 and 2 pair, or we could flip that around and do a bent pattern here. So those are all options for how we can make simple deadly patterns from this larger pattern here. And it gives us a lot of evidence that this whole pattern might be deadly if there's so many different ways we can create small deadly patterns out of it. Here's another deadly pattern that MythJellies also posted. This contains 5 candidates spread across 17 cells. And we could see there's many different ways to create deadly rectangles or those bent patterns in either 2x2 or 3x3 fashions. So again, not really proof that this is a deadly pattern in and of itself, but it's a good hint that this pattern might be deadly. So if you see a situation like this where you have a bunch of candidates which can be arranged into more fundamental deadly patterns, then there's a chance that you might have a permeable MUG on your hands. deadly patterns are what happen when we extend our avoidable rectangle technique from the beginning of this part to all the deadly patterns we covered so far. So just like how avoidable rectangles can be thought of as the opposite of unique rectangles, reverse deadly patterns are the opposite of deadly patterns. With regular deadly patterns, what we're focused on is preventing a certain pattern from being limited to a certain number of candidates, because then it will be deadly and impossible to complete. Whereas with reverse deadly patterns, we could say a pattern has already been completed with some of these candidates, therefore it can't be deadly and contain all of those candidates. So let's take a look at a couple examples here. Let's look at these 5 cells right here. It looks like we're almost forming an extended unique rectangle, and we would finish that pattern if we placed a 1 in this cell. However, that would make this a deadly pattern, making it interchangeable, and having at least one copy with a unique footprint. Therefore, we wouldn't have been able to fill in any of these candidates in the first place. Therefore, we know this cell is not a 1. We could say the same thing about these 8 cells right here. This almost looks like the BUG-Lite pattern with 8 cells and 4 candidates. And if we filled in a 2 in this cell, it would be that pattern. However, in order to avoid completing the deadly pattern, we can remove this 2. There are also reverse bugs, which are a little bit harder to visualize, and I've seen some competing definitions, but I think this grid, which was posted by RW on the new Sudoku Players Forum, is a really good example. So if we look at this grid, I want to focus on the 5s and 7s. So first, we could see our given 5s and 7s, which are in black here, and they form a deadly rectangle themselves. Now, according to our avoidable rectangle technique, the given candidates shouldn't be a problem at all, and we can't form any deadly rectangles with given candidates, so this shouldn't be a problem. However, if we look at our solved cells in the remainder cells here, we could see that our remaining 7s and 5s are all covered by the exact same 7 rows, 7 columns, and 7 boxes, which means they're effectively interchangeable. If we flipped the 7 and the 5 here, we would get the exact same footprint, which makes this a reverse bug because all of the placements of those 2 candidates are interchangeable. So this raises a really interesting question because our deadly pattern, which was created by the givens, created a reverse bug in the remainder, which means that givens, under some conditions, can actually be involved in deadly patterns. So let's look at this other example, which was posted by Aaron on the new Sudoku Players Forum. We could see this 5, 8, and 5 here. It looks like they almost form a deadly rectangle. Now, the avoidable rectangle technique would say you can't do anything with this because these are given candidates. However, if we look at all the cells in the remainder of these rows, we could see there are no givens. So if we were to complete this deadly rectangle by placing an 8 here, these remainder cells would then form one large deadly pattern because there are no givens to tell them which way to go. Because we have these same 7 candidates in the same 2 rows, so it's effectively interchangeable which row that they're in. Therefore, if we have we can form deadly patterns with given candidates if there are no givens in the remainder. And in this case, we could eliminate the 8 to prevent that deadly pattern. So that's how we would do reverse deadly patterns. Uniqueness clue cover, or UCC, is essentially a templating technique for uniqueness based on the distribution of given candidates, also known as clues. So basically what we could do is generate a template. If we have a certain distribution of clues, we could check that first the puzzle is still uniquely solvable. If it is, then we could look at any placement of a candidate in each cell and then check again if it's still uniquely solvable. And if that candidate makes the grid not uniquely solvable, we could eliminate that candidate. So we could generate all sorts of templates based off of this, and that allows us to generalize most of the uniqueness techniques we've covered. The problem with UCC is that you don't know if there are any uniqueness eliminations until you actually spot a deadly pattern. And at that point, it's easier to just use one of the techniques we already covered to avoid that deadly pattern than it is to hunt down a specific template based on the distribution of the given candidates. There is one important use case, though, for UCC, and that's when we have very few clues on our grid because there is a minimum number. For the whole grid, this minimum is 17, and that was proven in a paper by Gary McGuire from 2012, and I'll go and link that in the description. So if we have a puzzle and we have a suspiciously low number of clues, and we count it up and it's less than 17, we could just stop solving the puzzle because we know it won't be uniquely solvable. However, we could also have situations where we have essentially a minimum or near minimum number of clues in a specific region. As we saw with the reverse bug technique, if we don't have any clues for for two digits, then we can't solve the puzzle. And it's the same thing if we don't have any clues for two houses within a band. And not only that, if the clues form a deadly pattern, then we're not giving any useful information to the remainder of those two houses in the band, and we still won't be able to solve the puzzle. So whenever we have few clues, there's actually a lot of restrictions on where we can make um, subsequent solves because there are very few moves we can make to preserve a unique puzzle. So that's where UCC templates really come in. So to demonstrate that, here we have a grid from Sudopedia, and you can see we don't have many clues to start off with. It is more than 17, so this puzzle is still uniquely solvable. But if we look within this band, we only have 2 clues. And if you see that situation, alarm bells should be going off because um, there is a UCC template for 2 clues within a band. Same thing with 3 clues. And that template states that um, for the cell that is in the same column as your clues, but a different row, you could eliminate anything that's not one of the 2 digits of the clues you have. So in this case, we could eliminate anything that's not a 1 or 2. We could eliminate the 3, 4, 5, 6, and 9. And obviously the 1's already eliminated because it's in the same box. So we could actually place a 2 in this cell. And we could do the same thing with this cell. We could place a 1 here. So that is how we would apply the UCC template for 2 clues in a band, but there's also different templates for 3 clues in a band. So if we run to that situation, we could also apply UCC. And you could actually see the templates on that Sudopedia article. So anyway, that is how we would perform the UCC technique. And with that, we conclude this part on uniqueness techniques in Sudoku. As always, the links to all the grid references will be down in the description. If you enjoyed the video, make sure to leave a like. The next video will focus on combination techniques, which I'm defining as really a combination of everything we've learned in the series so far. That's going to include the ALS and advanced group techniques, the fish techniques, the chain techniques, as well as the uniqueness techniques we covered in this video. And that will be the last part of the series. So make sure to subscribe if you want to stay tuned. Thanks for watching.